I'd like to start off today by asking a question. Did anyone bring sensors with you today to the meeting? Yes? Show me how many of you have brought sensors. Like, for example? Yes, you got it. You got it. Okay. That's exactly what I was coming for. So if you have a smartphone with you, you brought not one sensor, but at least 15 sensors with you. It can be an accelerometer, it can be a camera, it can be a light sensor, it can be a touch sensor. That's pretty commonplace today, having a sensor on every person, walking, talking, in trains and airports, everywhere. You have sensors on you. So we call those smartphones, right? What about smart homes? A home like this, for example, is it possible that you're sitting at work and you want to know whether your home is safe or not? You want to know if there's a fire. You want to know if there's a burglar. Can you do this? And the answer is yes, because today you have remote sensors for all kinds of detection. Smoke, heat, light, motion, and so on. So you can have smart homes. We saw smartphones, we saw smart homes. I'm going to talk about something else that's smart. Smart food. What do you think of when I say smart food? Any ideas? It's okay, just say whatever comes to your mind. Smart food. Yeah, pesticides, detection of pesticides, yeah. That's one option. What I was coming to was smart food needing sensors for monitoring food all the way from the farm to the table, right? So let's start off with the farm. Analog Devices is a local company in Massachusetts where they initiated a project whereby local farmers could benefit from sensors that are instituted for growing tomatoes, for example, right? People want to know how much sugar is in the tomatoes that I'm growing, how much lycopene is in it, because that's the health benefit of tomatoes. Is there moisture in the soil where I'm growing the tomatoes? Are there pesticides in this area? What about the fact that I want to harvest the tomatoes? I want to pluck them. Are they ready or not? All of this is something that a farmer has to go out to the farm and check time and again. Is it okay? Is it not? Are there pests? Is there water? Is it fine for harvesting? Instead, Analog Devices came up with some smart sensors that could give all this information by wireless technology to a farmer so that the farmer can be physically removed from that particular area of the farm, but yet keep track of his tomatoes, right? So that is something that is very valuable, having sensors at food growth level. Now you grow your tomato. What do you do with this tomato? You have to transport it by trucks, by trains, by some way to the distribution center. Now during the transport, it may be a tomato we are talking about. It could be dairy, it could be fish, it could be meat, it could be poultry. You need refrigeration units, say, on the truck. And let's say that the refrigeration system on the truck breaks down. It's a huge loss to everyone involved if the driver of the truck doesn't know about it and just keeps driving from one coast to the other and delivers rotten tomatoes to the distribution center. So now you can guess what I'm about to say. I'll take a short break while everyone is seated. Come, please. Answer it on the go, okay? So for some of you who've just arrived, I'm talking about sensors, and right now we are talking about sensors for food quality monitoring. That's what I'm talking about tomatoes grown in the farm being transported in refrigerated trucks all the way to stores, like your big bazaar and so on. So now, if the refrigeration system breaks down, you're delivering rotten tomatoes to the store. Any ideas on what one should do in order to improve this scenario? Yeah, you have to have some kind of a way to ventilate, air condition your tomatoes, keep them at a certain temperature. But if it breaks down, you have to have a way to know about it. So again, you need sensors to tell you that this system hasn't worked. The driver doesn't need to drive all the way across the coast and deliver rotten tomatoes. Instead, he can dump the tomatoes and save everyone money rather than going through with the entire drop-off process. Yeah. So that's in the food transport network. You need sensors. From there, it comes to the distribution center. So right there is this market where you buy your tomatoes. There too, we need sensors. For what reason do we need sensors in the distribution centers? Any ideas? Why do you need any sensors there? Yes, exactly. If I'm owner of that shop, I want to know when to restock. If it's finished, you have a question? If it's finished, the tomatoes, I need to be able to restock the tomatoes. I want to reshelve it. Or I still want to know, is it fresh enough? And if I'm the person purchasing the tomatoes, I may want to buy organic tomatoes. And it's marketed as organic. I want to know, is it really organic or not? So again, you need sensors. So sensors are your extra eyes, ears, touch, smell sensors. Okay? This is what is useful in the distribution centers. Then you buy the tomatoes and bring it to your house. You put it in your own fridges at home. Again, the same thing applies. You want to know when you've run out of tomatoes, you have to go back to the store and buy some. You also want to know, are they fresh? Are they tasty? So again, you need sensors. So in this entire food cycle, from farm to the table, you need sensors. And this is what we call the smart food network. I'd like to talk a little bit about photonic sensors today. And don't worry, I'll explain each term that I'm introducing. So just starting out with the market. The market for global photonic sensors today is estimated to reach by 2020 almost $15 billion US dollars. So that's a large market for these photonic sensors. And photonic sensors just means that we are using photons or light particles to do our sensing work for us. Everyone knows about electrons. Well, this is another particle, which is a photon. It just is in the electromagnetic spectrum. It's a light particle. Let's look at some of these characteristics here. Oops, sorry. Where's my pointer? Yeah. Global photonic sensors by product type. You may not be able to read all of this very clearly, but I'll just point it to you. For example, here this tells me that fiber optic sensors are leading in the market compared to the other sensors. This little chart here is telling me that Europe is the leader as far as accepting global photonic sensors. And here this tells me that perhaps industrial processes are the ones that use sensors, photonic sensors, the most. Why? Why is it that photonic sensors has suddenly taken off? Well, two big reasons, and that's shown in this final chart here. The two top impacting factors why global photonic sensors have taken off is wireless technology has reached very, very sophisticated levels today. We use wireless in everything today. We have Bluetooth, we listen to music, we have wireless technology at our fingertips. So that's one reason. Another reason is there's a great demand for security and surveillance in our communities today. And so these two big reasons have mushroomed the need for sensors, and particularly photonic sensors. Now I'm going to go down a little bit deeper. Started with sensors, went down to photonic sensors. Now I'm going to go down even further to integrated photonic sensors, and that's an image of an integrated photonic sensor. How many of you here are familiar with, say, integrated VLSI or integrated electronics? Almost everyone should raise your hand, actually, because you all use your phones. You showed me your phones earlier today. They all have computer chips in them. Your computers have little chips in them. All of these chips have nothing but integrated circuits inside. And this is an example of such an integrated circuit. Only difference between an integrated chip that's in your phone and this thing that I'm showing you is this transports light, and those transport electrons. So that transports, you have current flow, here you have light flow. That is the big difference. Okay. Now, this integrated photonic sensor, the way I describe it to those who have not heard about integrated photonics before. Has anyone heard about integrated photonics? No. So then I'm okay to explain it at a better level. Integrated photonics you can assume as a fiber optic cable on a chip. So if you bring fiber optics to a small micron scale, that is what integrated photonics is all about. So right here, what I show you is a small chip that's micron sized, few micron sized, on a chip, and its job is simply to transport light from one end of the chip to the other end. And in between, whatever happens to it is registered at the output. So that is my sensor. That is my integrated photonic sensor. And the applications I'd like to explain are very diverse. Let's start off with Internet of Things. Internet of Things is what I discussed when I talked about smart homes or smart food. You need sensors, and you need a network of sensors that can talk to each other. I may have a sensor growing on put on my tomato. I can have a sensor next to it on brinjal. I can have a sensor on other crops and so on. But I'd like them all to communicate with one another, so they're an interconnected network of sensors. So that is the Internet of Things. That's the beauty of the new Internet of Things. They can all communicate with each other. Another place where we need sensors is industrial pollution monitoring or just industrial processes. In all of these cases, we need sensors. Integrated photonics gives you the option of making everything small and perhaps lower cost. So you get everything that you get in a large sensor, but in a small footprint and at a lower cost. So industrial pollution or process monitoring, food and water quality monitoring. You need sensors to tell you whether the water you're drinking is safe or not. The food, is it ripe or not to harvest? Does it have any pesticides? Is it organic? Then oil and gas industry needs sensors to say if there are any leaks in a pipeline. Automobile industry, nowadays you have Google smart cars. They have sensors everywhere around, top, side, left, behind, and you know exactly when the next car behind you might hit you. Those kinds of sensors are also very useful, and integrated photonics can make such sensing happen. Medical industry, it's everywhere. You need it for diagnostics, for imaging and other applications. You can make integrated photonic sensors, especially sensors where light is able to do all the detection for you without poking with needles. So non-invasive kind of technology is usually with light. And our usual favorite, which is security and surveillance. All of these diverse applications and many, many more, which I didn't go into, are possible with integrated photonic sensors. Now I'm going to go further down even more and talk about integrated silicon photonic sensors. And why do I care about using silicon? Any thoughts why I'm introducing silicon photonics? Exactly. It's very well developed. Everyone knows about how silicon chips are made and how they work. And the advantage is, if I use a silicon chip and put all my photonics on top of it, the photonics talks to the electronics. And now I have a direct communication. I can send all my signals directly from the silicon. So that makes it even more efficient. So now I'm going to talk about, this is my topic for today, mid-infrared, integrated silicon photonics for sensing. The only word here that I have not discussed previously is mid-infrared. And I will tell you in a minute why we go into mid-infrared. But this is what I'm going to talk about today. My name is Anu Agarwal, and I have been working at the MIT Microphotonics Center for almost 20 years now. Very recently, as was pointed out, I have also started working in what's called the Advanced Institute of Manufacturing for Integrated Photonics. This was an institute for manufacturing, started out by President Obama in his vision of trying to bring more high-tech manufacturing to the United States. And this is why we are trying to build a platform of high-tech manufacturing using integrated photonics. In my case, I'm trying to make integrated photonics for sensors. So mid-IR, remind me if I don't get to that, but that's the only term that I have not introduced so far. So here's the sensor, a schematic, of course, of a sensor on a silicon platform. You see that there is my light source. If it's a photonic sensor, there have to be photons, which means that something has to bring the photons to the chip, and that's my light source. It can be an LED, it can be a laser, it can be any of a broadband light source. Then that light has to be transmitted along the chip. The red that you see, those are the fiber optics on a chip, or what we call waveguides. They guide the light wave on the chip. And that leads to the circles that you see. These circles in blue are what we call the sensing elements. It can be anything. It doesn't have to be a circle, but I've just demonstrated it here as a circle. And these sensing elements, what do? The light from the red waveguides, I've shown it in red, the light from this is actually made by my student, and he had a nice sense of humor. He said, oh, infrared light, so let me make the light waves red, the waveguides red. So that's why we have a red image here. So light comes from the light source through these waveguides and interacts with these circles, which are the sensing element. So when light comes through and interacts with my sensor, what might happen if I have a chemical in that area? Let's say I have methane gas, which is an environmental pollutant. It is a gas that leaks from oil and gas pipelines. It's a very common gas around here. If there's that methane gas and my light is passing through the waveguide and my sensing element, suddenly the light that is in the sensing element, some of it is in the environment, it sees the methane gas, or rather, the methane gas sees the light. And if the absorption of that methane gas lies in the range of the wavelength that we are sending through, the color of the light, the color of the photon, if that matches the wavelength that methane absorbs at, you find that what comes out at the other end is less than what you started with. So that is the sensing mechanism. It tells me something about what happened at the level of the sensor. Always remember that electrons are easy because there's only one kind of electron, whereas photons have many colors. There are so many different kinds of photons, different wavelengths, and that's why it's a little bit more complicated. But because of that complication, it also has an advantage because every gas molecule has a different vibrational energy. Let's say CH bond. People here heard of CH bonds, carbon-hydrogen bonds? Yes? Yes. So this vibration of the carbon-hydrogen bond happens at a certain energy. If that energy is matched with the light that's coming through, that wavelength, that lambda of light that's coming through, that is what gives the photonic sensor its ability to detect specifically what is happening, what gas is there. If you have just an electronic sensor and it's changing its voltage, you can say, some gas went over my sensor, but I don't know which one. Whereas if it's a photonic absorption sensor, you know exactly which gas because methane absorbs at a different color, propane will absorb at a different color, butane at a different color, and so on. So you can get exactly what gas it was that went over the sensor. So that is the sensing element. And of course, you also need the final element, which is the detector. In this case, we use some material called lead telluride, and I'll tell you why again. Ask me if I forget to tell you, but I think I will remember. So you take the light source, this light goes through the waveguides to the sensing element, all the detection happens there, and then it goes over to the actual electronic detector. So right at this point is where all of the light energy is converted to electrical energy, and you get a voltage signal, either a photovoltage or a photocurrent signal. And that's what you monitor. Once you get that signal, then you send it through an RFID chip, which is connected in a network of sensors. And when you have this interconnected network of sensors, now you can imagine the same chip, hundreds of them, interspersed wherever you're looking, and all of them talking to you and talking to each other, giving you a wealth of information that you could not find if you had a big sensor sitting in one spot. So now you have a network that's spread around, all right? So you have an RFID chip that includes the connectivity of the sensor. And now I want to talk about something very important. As a material scientist, for me it's very important to decide what material should I pick in order to make my sensor. Should it be silicon? Should it be silicon dioxide? Should it be silicon nitride? Should it be something else? So now comes the investigation that I've got to go back to the lab and do. What material should I pick to make my sensor? Now I'm going to go back to that word which I left out so far, mid-IR. If I'm going to make a sensor that transports mid-IR photons, basically photons which have a wavelength of 3 microns to about 5 microns of wavelength,